Hey guys, welcome. So in this video we're gonna have a second look at fields, but I already dedicated a video to introducing fields, spelling out what is required to be a field, right? I also have videos introducing groups, and actually just more than the introduction to groups, but I have a video on rings and integral domains, and so if you watch all of those, you can see the progression from groups all the way to fields, and all it is like more structural requirements on your set, right? Okay, we know that groups come with only one binary operation, whereas rings and beyond come with two binary operations, right? So this video is going to be as much about reinforcing what we know about fields as it is, like delineating between these guys, right? So showing like examples and basically a race to the field, as you'll see. All right. Let's get started. Now, as I've already said, rings, integral domains, and fields require a set together with two binary operations, and in the introduction video to fields, we looked at this Cayley table together with this Cayley table, and we said that between the two of them, we have a field. So really, a field is like two groups, one with multiplication and one with addition, put together. Yeah? Okay. So that's kind of like a nice summary of what fields are. All right, okay, our examples are going to be this, and what we're going to do is we're going to lay out three different sets and see who makes it all the way to the field. And the first is going to be 2x2 matrices with real entries. So A, B, C, D, where A, B, C, and D are in R. Right? And I don't want to enter the territory of rings, and so I don't want to write A, B, C, D, and R here. So just keep that in mind. And the second is the integers mod n. So the integers modulo n is our second set, right? And once we cross over to rings and so on, we will add, in addition to plus, we will add times or multiplication, right? Okay, I've already said enough about that. And the third is the set of complex numbers. Yeah? Okay, so first of all three of these sets form an abelian group, right? And before we go to rings, we need to first be an abelian group. And you can check, but the set of 2x2 matrices, the integers mod n, and the complex numbers are all an abelian group with respect to plus. I should have said it's with plus, but you also should understand, I already mentioned that groups come with plus, right? Okay, so abelian group with respect to plus. And so who makes it to a ring? Well, what extra requirements do we have past groups to become rings? Well, we require that star be associative, that is multiplication be associative, but also, more crucially, we require the distributive property of times over plus, right? So star over plus. So we need, for example, for 2x2 matrices, we need that A times B plus C, where A, B, and C are 2x2 matrices, we need this to equal A times B plus A times C, right? That's the crucial additional requirement past the abelian groups that makes you a ring, right? And that's true for the 2x2 matrices. It's also true for the integers mod n, and it's also true for the complex numbers. So everyone advances to rings first. They're all abelian groups with respect to addition, but everyone advances to rings. Okay, what about integral domains? Well, you see, between rings and integral domains, wedged in really is a commutative ring, right? So before you can advance to being an integral domain, you need to be a commutative ring. And of course, when we say commutative ring, as I've already said in previous videos, we're talking about star or multiplication being commutative. Otherwise, we already said they all have to be abelian groups with respect to plus, right? So here, we need star to be commutative. But wait, we know the matrix multiplication is not commutative, right? And that's generally true for matrix multiplication, and therefore true for 2 by 2 matrices. So 2 by 2 matrices, we can come up with examples of why they're not commutative. So we can come up with counter examples to the claim that 2 by 2 matrices are commutative, and therefore 2 by 2 matrices cannot make the cut for integral domains. What about the integers mod n? Well, they fail to be an integral domain, as I've already showed in the video on integral domains. The integers mod n fail to be integral domains because, well, they have what are called zero divisors, right? And zero divisors are like, for example, as I did in the video on integral domains, if we take mod 8, then 2 times 4 is equal to 8, which is 0 mod 8, right? It's 0 mod 8, right? So integers mod n have zero divisors, because having a zero divisor means you multiply 2 non-zero things and get to 0, and that's clearly true here. So the integers mod n do not make the cut for integral domains. Now, if n is a prime, if n here is a prime, the integers mod n do make an integral domain, because, well, when n is prime, mod p of prime, you don't have zero divisors, right? And that's because of, primes being what they are. All right. But the complex numbers do form an integral domain because, well, again, I'm not saying too much about the requirements for integral domains because I already have a video dedicated to it, but they are commutative rings with unity, which is like a multiplicative identity different from the additive identity 0. So like something that acts like 1 does with respect to multiplication, and of course no zero divisors. That's what makes you an integral domain. And the complex numbers, it turns out, are an integral domain. So they make it here. Because if you have 2 complex numbers, z1 and z2, and you multiply them, the only way to get to 0 is if either z1 is 0 or z2 is 0. Yeah? Okay. Of course, the number 1 acts like the multiplicative identity, and yeah. And of course, complex multiplication, complex number multiplication, that is commutative. So the complex numbers do form an integral domain. So who makes it to the field? Well, only one of these guys has any hope of making it to a field crossing this line, and that is the complex numbers. So what's the additional requirement from integral domains to cross over to fields? Well, we need multiplicative inverses also, right? So in addition to a multiplicative identity, we need multiplicative inverses to become a field once you are an integral domain. And the complex numbers do have multiplicative inverses, because if the complex number z is a plus bi, then we can claim that z inverse is x plus iy, and we can define z inverse in terms of a and b. So we can define x and y in terms of a and b, and the way we do it is I don't need this space. I need the space, but don't need this writing anymore. So this is how I think I already have a video on showing you the inverse of a complex number, but a generic complex number, a plus bi, but this is what we'd have to do, right? We'd have to take a plus bi, multiply it to x plus iy, and we need to equal 1 plus 0i, right? Then x plus iy we can claim is the inverse of a plus bi. Now, so if you do the multiplication, you get ax plus a yi, right? And then plus bxi, and then minus by equals 1 plus 0i, right? Okay, cool. So that means that ax minus by needs to equal 1. So the real part of the left side, which is this guy and this guy, need to equal the real part of the right side, which is 1. And then ay and then plus bx needs to equal 0. So the imaginary part needs to equal the imaginary part, right? Okay, now remember what we said is having been given z equals a plus bi, we need to find z inverse in terms of a and b. And so this is how you do it, which is solve the system of equations in two unknowns. Yes, I did not misspeak. I said two unknowns because, well, we supposedly know a and b, so here what we're solving for is x and y, and so, like, you know, you could do elimination. You've solved system of two equations and two unknowns. You could do elimination or substitution, and you'll be able to define x and y in terms of a and b. Yeah, okay, cool. Yeah, I think that's it. Keep watching. I hope you enjoyed this. Take care.